line from the lowest, all the way from the lowest frequency to the highest frequency, and it has a slope. You see, over 1 decade, it goes 20 dB, so it's 20 dB per decade. And so it's just, the general form is S over omega 1 raised to the n, and the n value is just 1, right, because this slope is 20 times 1, basically. And the omega 1, that's the 0 dB crossover frequency, and so it's S over 1. And then at 10, there's a break, there's a change in slope, and the change, it goes from 20 to 0, so that's a 1 plus S over 10 there, raised to the first power. And then at this frequency here, notice that it goes from 0 slope to minus 60. In other words, this level to this level, that's a change of 60 dB over 1 decade. And so 60 dB per decade, that's 20 times 3. Actually, being a negative slope, it's 20 times minus 3, so that this would be, you could express it as 1 plus S over 10 raised to the minus 3, or 1 over 1 plus S over 10 raised to the plus 3. And then at this point, you got a change in slope. It goes from being minus 60 to 0. And so it would be a numerator factor. It's a positive change in slope. So it's 20 times 3. So it would be 1 plus S over 10 cubed raised to the third power. So that's the transfer function. And you could have other, in other words, a plus or minus here, 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 and so on. The magnitude doesn't change. So, and then there are a couple of ways to so this is the basic equation for a straight line. It's y minus y0 equals m times log of x minus log x0, because we're dealing with a logarithmic scale, and the log is base 10. So you can use either x1, y1, which it would be 100 and 20, that point up there, or this point over here, which is x2, y2, which is 1,000 frequency and a magnitude of minus 40. So, using x1, y1, you got this. You got 20 minus 0 is equal minus 60 log 100 minus log omega x, and so you just simplify that. Divide by minus 60, you get minus 1/3, and a log of 100 is equal to 2. And so you have that, and so you find the log of x, it's 2 plus 1/3, or 7/3, and so omega x is 10 raised to the 7/3, 215. Or you could use this one here, and that's the same idea. y2 minus y equals m log x2 minus log x1, and just substituting in the values there. We're going through the similar operations. Any questions about that? So the next problem. What we had was 2 poles. You see at s equals 1, we have pole, 0 at the origin, right? And so we wanted to draw the root locus for this. And what you can do first is find where the root locus exists on the real axis. And so being a double pole here, that to the left is this point here is to the left of an even number. So the root locus does not exist here. Here, anywhere here. the root locus will exist. There's 1, 2, 3 points to the right of that test point. Okay, so root locus exists there, and then it's going to it can't move. It can't exist here or here, so it's got to break away. There's really no other possibility. And it has. You have to remember that. Okay, here there is one asymptote, right? The the difference between the number of open loop transfer function poles and zeros is 1. Right? It's an S squared denominator, second order denominator, and first order numerator, and the difference is 1. So that's one asymptote. And when there's one asymptote, the angle of the asymptote is always going to be 180. And so you know that there's going to be an asymptote on the negative real axis. Okay. And so, and the root locus exists on that asymptote. And so now, you also have to keep in mind that the root locus starts at the open loop transfer function poles, that's with k equal to 0, right? And it ends up at the open loop transfer function zeros. There's one finite 0 and one 0 at minus infinity, at the end of that asymptote. Okay, so it's got to re-enter. Okay, and then one branch will move towards that finite 0, and the other branch will be directed towards the 0 at minus infinity. And, you know, I didn't ask for it, but this turns out to be a circle whose radius, whose center is actually the 0. The center is the 0. Okay, so any point on this root locus here is at a radius of 1. You can find and this is the asymptote. Here, the characteristic equation, you can find the breakaway and reentry. Obviously, the breakaway is right there at k equals 1. And if you said that, hey, this is a circle of radius 1, you would know that the reentry point is also minus 1. And that the crossover, the omega axis crossover, would be J1, because the radius is 1. But here, you can do the dk ds set equal to 0. You get this quadratic here, which factors into this, and so the solutions are 1 and minus 1. So the breakaway point is 1, the reentry point is minus 1. And this was, I just found the J omega axis crossover point. I didn't ask for that, but you could do the Routh array, and you find the characteristic equation, do the Routh array, then set this term to 0. So k equals 0, you could form the auxiliary equation from the previous row elements, and it would be s squared plus 1 s squared plus 1s to the 0, and so s equal plus minus j1. For stability, k would have to be greater than 2. And that's kind of clear here that there is a region in which the system is stable. Apply the angle condition and graphically represent all angles involved. Determine whether s equals whether this point lies on the root locus. Turns out that if you find the magnitude and phase of this, magnitude of 1 plus j1 is square root 2. Square root 2 at angle 45, and you divide by square root 2, so it's at 1 angle 45. So that point is on the circle, and so automatically it would lie on the root locus. But here you can do it a couple of different ways. You can draw a vector from each of the poles and the 0 to that point in question. And so you then determine the angles involved. These are the angles relative to the positive real axis. So it would be this angle, these two angles here because you have two vectors, and that angle there. And so you can find this angle here is going to be 180 minus the arctangent of the square root to the imaginary over the real. The real is 1 minus this 1 over square root of 2. And so that gives you 67.5. This gives you 112.5. And you multiply by 2 because you have two vectors from the double pole. And this 0 here contributes 45 degrees phase. So applying the angle condition, you got the phase angle due to the 0, which is 45 there, minus the sum of the phases phase angles due to the poles. And so you have two poles at the same point, so it's minus 2 times this difference here. And you check to see whether that equals 180. And so this turns out to be minus 180. And so it does lie on the root locus. Here's another way that you can, you have the G of S. You can simply substitute the S value in there and evaluate the phase. Here I just evaluate the magnitude and phase. But the phase, if it turns out to be 180, then it's on the root locus. And so you have magnitude and phase for this factor here, and then substituting the value of S in there, it becomes minus 0.293 plus J1 over square root 2. And so you take the square root, well, it's squares, and so you take the square root of the sum of the squares times the square root of the sum of the squares. So it just gives you this factor here. And this is e to the j theta 1. If it's 1, raised to the first power, e to the j 2 theta 1, because it's raised to the second power. And so this theta 1 is as we saw before. You see, it's in the second quadrant, minus 293 plus J1 over square root 2. So it's going to be 180 minus the arctangent of the imaginary over the real positive. And so it gives you that. And so it turns out really the same as what we have up above there. So first, it asks for the angle deficiency, the positive phase angle that the lead compensator has to contribute in order to satisfy the specification that the closed loop transfer function pole be located at -1 plus or minus J1, this complex conjugate. And so you can apply the angle condition to find this angle deficiency. It's really just the difference between the numerator phase of the compensator minus the denominator phase. And first of all, if you make a diagram, it's very helpful. Okay, you draw a vector from each of the poles, and notice that the 0 is right on top of the pole, and so effectively they cancel out. Okay, this cancels with that. Okay, so there's the phase of the denominator factor of the compensator. The numerator phase of the compensator, due to that 0 of the compensator, is 90 degrees, the numerator phase. Okay, so you got, you got this positive 90, there's a zero, minus the sum of the pole phases. And so theta p is what, you know, you're looking for, minus 90 for this pole there, minus this angle theta 1, which is 153.4. So you can find theta sub p, and the angle deficiency is the difference, that is u minus theta p, or 63.4. Now you want to find b here. And actually you can find it by inspection, right? You notice that this one here is a distance of 2 from the desired location for the real component of the closed-loop transfer function pole. So this b should be 2 units to the left of minus 1. And so b would be minus 3. Sorry, b would be 3. And analytically, you know, you have this theta sub p was 26.6, right? So analytically, the tangent of 26.6 is the imaginary over the real, and the real would be this minus that, right? In other words, actually it would be 1 minus b. Okay. In other words, this distance in here would be 1 minus b. Okay. And so you can solve for b. B equals 3. Is that right? Mm-hmm. I think it's minus 1 minus b. Okay. Because if b is equal to 3, yeah, okay. 3 minus 1 is 2. Okay. So actually then it would be this minus 1 minus b. Okay. Or you just call it x. Just call it x. Right? And so you find x would have to be equal to 2, right? And so if that's 2 units, that distance there, then that has to be minus 3. Okay. B itself would be 3. And now here you can find the corresponding value of gain k. You use the characteristic equation. Right? So solve for k from the characteristic equation. You have the pole, the 0 and the pole, they were canceled. Okay.
Professor?
Yeah.
How come, could you just explain to me why that, when you find the angle of theta 1, how come it's a positive 1/2?
The theta 1.
Negative, that's where I messed up.
The plus 1, you're talking about this one?
In the upper right-hand corner to the...
Upper right.
Yes.
Okay. Yeah. Because this distance is 2.
Okay, so, all right. So,
So the imaginary is 1, the real is 2.
okay.
So that this angle in here is our tangent of 1/2. And this angle would be 180 minus that.
Okay.
That's okay?
Yeah, okay, I see what you're saying. Thank you.
So then we find the k here. The k, and from this characteristic equation, you evaluate it at the desired closed-loop transfer function pole. And you can do it a couple of different ways. You can express it as the k is the magnitude of s plus 3 times the magnitude of s minus 1, or you can just use this as it is, substitute the value of s. In both cases, you would substitute the value. You've got to substitute the value of s. I'll show you. Here, you substitute the value of s, and you can find k equals 5. over here, you've got the s plus 3, think of it as a vector, and the s minus 1 as a vector. The vector s plus 3 would be from there up to the desired point. And what is the size of that vector? As this is 1, this is 2, and that's 1. It's going to be the square root of 5 by the Pythagorean theorem. Right, square root 2 squared plus 1 squared, square root. And similarly, the other vector, the s plus 1 vector. And so here we're talking about the pole at s equals 1. So this vector here also has, it makes sense because the whole diagram should be symmetrical around this point here, right? If this minus b is actually minus 3, it's moved over. If I drew it correctly, it would move over a little bit, right? And be a perfect triangle, or kind of, what do we call it, isosceles triangle. So without substituting specific value of the s in there, you can look at that, and once you realize that b is equal to 3, you say this has to be equal to, this vector has to be the same size as that vector, and this vector is the square root of 5, therefore the other vector is square root of 5. So you get 5. And this part here, I gave it as an extra credit, so the part A is in total 25. And this was kind of extra credit. Decided to do that. And so if there's no exact cancellation, the 0 will lie either to the left or to the right of that hole. And therefore, automatically, you've got a branch of the root locus in the right half plane. K equals 0 at the pole, k equals infinity at the 0, likewise over there. And for the closed loop control system, we will have a pole on this range in here, not there and not there, because k has to be greater than 0 and less than infinity. It has to be in there somewhere. So you will have if you don't have exact pole 0 cancellation, here you have an unstable system, because you will have a closed loop transfer function pole in the right half plane somewhere on this region. Okay. If it's in the left half plane, it's okay if they're not exactly right on top of each other. Okay. Your analysis, your result will still be good. Proximate, but useful. So you understand that point? You understand that point? A lot of you talked about stability. I try to give some points about it, but this is specifically, I think, the explanation. So this is a different approach in solving the problem. You know, you start out with the characteristic equation, and you express it. This is a characteristic equation in terms of B and K. And then you have the desire. How do you get the desired characteristic equation? You know where the desired poles are, so you can express the desired characteristic equation as S minus S1 times S minus S2. Okay. And And so substituting in the desired poles, you get this desired characteristic equation. And so then it's just a matter of equating corresponding terms or factors in that characteristic equation in terms of the parameters that you're looking for and the numerical characteristic equation. So you get B equals 3 and K equals 5. And so that would be the compensator. That would be used to satisfy the specification. In other words, to place a pole of the closed loop control system right at -1 plus or minus J1, the complex conjugate poles. I mean, we control the root locus for the whole thing. We control the root locus. It turns out to be very simple, right? Because we use pole zero cancellation, so it looks like a cross. Right? And we have what was it, 1? We have pole of 1, and we have to have a pole, and this is -1, -2, and -3. Pole there. So, and this is -1, -2. And so the root locus looks like that. And when this is J1, right, and K has to be adjusted to 5 in order to get the desired closed loop transfer function poles at those two locations there. So, pole zero cancellation makes the root locus simple for this second order case. And in this problem, it says desired value of the static velocity error constant is 10/3, and so giving justification, find the numerical value of beta. And so we're given the compensator in terms of T and beta, and so it's just using this formula here. So the KB hat, this is the compensated static velocity error coefficient is this limit. And you see when S goes to 0, the T's cancel out, and you have a beta in the numerator and a 3 in the denominator, and that's equal to the 10/3 there. And in the second problem, what it was asking for was the phase contribution of the lag compensator at those points. At those points, you just need to choose one of those points, right? Say -0.4 plus J.4. Substituting that in, you get this numerator denominator complex numbers, and you can express each one in terms of magnitude and phase, and so the phase is going to be, you've got theta 1 here, and you have a similar diagram for theta 2, except it would be minus 0.39 here. And so in each case, it would be 180 minus the arctangent of 0.4 over 0.37, or arctangent 0.4 over 0.39. And so you get 132. So I noticed that some people inverted it. So it's imaginary over real. And so 132.7, and then over here is minus 134.3, say. And the difference is minus 1.5. And this lag compensator, you see it's quite a bit different than the lead compensator. The lead was used to satisfy a desired closed-loop transfer function pole specification, and so it dramatically moves the root locus from before to after. Remember, before, as far as the root locus was concerned, it started out, we had a pole at 1 and a pole at minus 1, I believe. And so it would be a cross, but it would break away at minus 0.5. Is that true? No, it would break away. Where would it break away? If it's plus 1 and minus 1, the poles, it would break away right at the origin, right at the origin, and then break upward and downward. And so the lead compensator shifted it significantly, whereas the lag compensator, remember the lead compensator contributed a positive phase of 63.4. Okay, the lag compensator contributes very little phase. So what that implies is that the desired closed-loop transfer function pole doesn't move very much at all with this small negative phase contribution of the lag compensator. And so, but what it does do is increase the steady state ramp error accuracy in this problem here. Are there any questions? Yeah.
Will you be uploading the solutions to what?
I'm going to upload it, yeah. I'll put it on, I scanned it, I'll upload it. Okay. Any other questions? Any questions about the homework? What's your question?
Remember, report, or actually, so for the first one, number one, the function is 3 over s times s plus 1 squared. And then, so you give us the table for frequency, magnitude, and phase for the first one. I'm just wondering for the phase, some of the numbers I'm just like trying to use, like, you have negative 90 minus 2 tangent inverse omega. And so I'm just wanting to see like where you getting these numbers from. Like is that negative 90 coming from the s by itself on the outside, and then is the 2 times tangent coming from the square?
Yeah.
Okay, so
Yeah.
that'll help me with the other problems that I haven't finished yet.
That was,
Yeah.
that's right. And so you want to find the expression for magnitude and phase when S is replaced by j omega.
Yes. So I understand the magnitude part. That was good. Just the phase.
Yeah. So this becomes 3 e to the j 0, right?
Yeah.
It's 3 angle 0. And this is equal to omega and e to the j 90. Right? Because when you replace s by j omega, right, you've got it's along the positive j omega axis, right? This is j omega, so it has a phase of 90 degrees.
Yeah.
Right. So this one omega is positive, right? And then this is 1 plus j omega quantity squared. Right? So we can express this as 3 e to the j 0 omega e to the j 90. And when you bring it up into the numerator, it becomes minus 90. Okay, and this one here is going to be the square root of 1 plus omega squared, and it's going to be e to the j, say, call it theta 1, where theta 1, actually, this is going to be squared. Theta 1 is equal to the arctangent of omega over 1.
Right.
Right, and so this becomes e to the j 2 theta 1, so the phase is going to be minus 90 minus arctan of minus 2 arctan that.
So that 2 is just coming from the fact that it's quantity squared.
Yeah,
Okay.
because this, when you square this, you get e to the j 2 theta 1.
Thank you. That makes sense.
Is that it?
Yeah, that was it.
Any other questions? So just be careful with your math, and that, that's an important step.
The first two I didn't have much trouble with.
Yeah.
The last two,
Last
the
two.
3 and 4,
Yeah.
I had some trouble with kind of just figuring out the shape of them.
Yeah,
Like I put them in MATLAB, and that doesn't really show the whole thing.
yeah. MATLAB is
It
not
gives,
going to show
it
you.
gives a good indication of, what it looks like near the origin, but
Yeah,
it doesn't show the stuff with infinity.
It doesn't show the infinity part. But let me get it. Here I have it. Just for a second, I'll find it and then bring it up to you. Okay, so B3A. So this is what we have. We want to draw the microcycline, right? And all I did here was just show that it is stable. Okay, and then here we have to take a look at that, and so. Here's one. X plus 1 over S squared. We have to route around that pole to origin, right? And so in the S plane, the contour has to go around like that. And this is S equals rho e to the j theta, where rho is going to be going to 0 because we want to enclose the whole right half plane. And so we want to exclude the double pole at the origin. And so we're going to start here and stop here. That'll be segment 1. and then we'll start here and stop at J infinity, and that'll be segment 2. And then we'll start here, and we'll go all the way around and come back. But if you just go around this segment here and take the mirror image of what you get, and then you'll have the complete Nyquist diagram. Okay, so the first step then is to replace S by rho e to the j theta. So we have g of S, where S is equal rho e to j theta is equal to 1 plus rho e to the j theta divided by rho e to the j theta quantity squared. So now we have to take the limit because rho is approaching 0, rho, right? And theta, you see theta is this little angle in here, theta. Theta varies from, we're going to start here and then end up there. So theta varies between 0 and 90 degrees. Okay. So this right here, notice that when rho goes to 0, you can throw this term away. All you're left with is 1 up there. Okay. And down in the denominator, what you have is 1 over rho squared. Rho is going to 0, so you'll have 1 over 0 is infinite. But don't throw away the exponent. Okay. It's going to be equal to infinity e to the minus j2 theta. Okay. Where theta, it varies between 0 and 90 degrees. So this is the S-plane here. We're mapping from the S-plane to the GH plane. And we are looking for encirclements about the point -1. Okay. And so when you do this, notice that when theta is equal to 0, it starts at infinity. Right? This point is at infinity. And then as theta increases, it goes around down like that all the way over to there because theta is varying from 0 to 90, and so this one varies from 0 to minus 180, but it's 2 times 90. So it comes around like that. This is segment 1 prime. Okay, that's the direction. Corresponds to this direction here. And the next step is to set S equal j omega. So we've got step 2, g of j omega is equal to 1 plus j omega divided by minus omega squared. Okay, and then what you want to do is use the frequency response to help you map this segment. Okay, and the frequency response tabulation is this, I believe. Right? It starts at minus when the frequency should start to be greater than 0 because we don't start right at 0. We have to route around that. Start at some frequency greater than 0, increase the frequency from low to high. Notice that the phase decreases while the magnitude, let's see, actually the phase is increasing, right? It goes from minus 179 to minus 90. So it's increasing. And the magnitude is decreasing. And so, it's going to start off with this one left off. This one left off at that point there, minus j infinity. Okay.
No, we're on this.
Over here. It starts out there, and it's if you plot some points, it's going to look like this. If you plot some of those points there, okay, for example, point 1 angle minus 95. And again, you've got a distorted plot because you're trying to plot large magnitudes as well as small. Okay, so you'll get, say, a vector whose magnitude is 0.1 and whose phase is minus 95, right? So that 0.1, 95.7. So that might be approximately there. But this is the mapping corresponding to those points there. And the next step is to move along this trajectory here. And along this trajectory, S is infinite, so you basically have S over S squared, which is 1 over S, and with S infinite, that's 0. So all of these points here map into the origin. And at this point, remember, it's minus infinity. Right? Minus infinity. So now we just take the mirror image of this. Right? And so we get this and that. And so the direction is consistent. Okay. In other words, we move along this contour here. We're right there for this whole contour movement. And then when we start from minus J infinity and move up, we're talking about frequency is negative frequency, minus infinity, and going towards 0 frequency. Okay, it's going to give us this segment right here, right? It's going to give us this segment here as we move up from that point to that point there, and then mapping this segment here is going to give us that there. So really, all you need to do is map only half, right, the upper half. This, segment 1, segment 2, and segment 3. Segment 3 starts there and ends there. And now take the mirror image. Right? The mirror image is going to be this and that. Okay, the point minus 1 is in there somewhere. It's got to be, this is minus infinity, that's 0. And so, what is n equal to?
0.
Yeah, you can, if you start here, you have to end there. 1 counterclockwise, 1 clockwise. The net number of clockwise encirclements about the point minus 1 is equal to minus 1 plus 1 equals 0. And P, remember the definition, is the number of right half plane poles of the open loop transfer function. And there are no right half plane poles. Therefore, P is equal to 0, and therefore Z is equal to 0, and therefore the closed loop system is stable. So you saw how we used the frequency response calculation. Yeah.
So how come that plot doesn't look like MATLAB?
You can, it gives you like that little sideways parabola.
The MATLAB plot is going to look like a little bit like, it's going to look like this. Basically, you got to fill in. Yeah, and that's why it's important to understand what's going on. When you take a look at MATLAB, you can say, hey, all right, this is right around the origin of the loop transfer function, right? And that's what you get. It puts these arrows here. So it's really giving you the frequency response segment of this. Okay. It can't plot all the way out to minus infinity. Question number 4.
I can use that one on my own.
More.
I'll try that one on my own.
Oh, okay. Any other questions? So I think it's due tonight. If you don't have any other questions, I hope you have a happy Thanksgiving. That's fine. So next week, so next week we have Monday and Wednesday. So we do mainly review, right?